Hey guys, today we're going to talk about Hooke's law. Hooke's law has to do with springs, and it relates back to the elastic potential energy that we introduced when we first started this unit. So our current definition of work applies when we have a constant force acting on an object. But more often than not, the forces present are not constant. So that's an ideal situation, and most of the time it doesn't actually work that way. Specifically, springs allow a force to act on an object, but with varying amounts of force as the object moves. So as it starts moving, or as the spring is slightly compressed or stretched, it's a lot easier versus when it starts getting very stretched and compressed. So springs allow work to be done, but at a varying amount, not a constant amount. The more a spring is stretched, the greater the force is required. And there's a relationship between these two factors, which is called Hooke's law. When a spring is stretched, there is a restoring force that is directly proportional to the displacement of the stretch. So here's the equation for Hooke's law. The force is the opposite of the spring constant times the distance. Now this opposite is just directional. I'm not going to be picky about it when it comes to equations because it just tells me that it's the restoring force or the force that it feels as it goes backwards. So for our math purposes, you could just use k times x. And remember, k is the spring constant, and that's measured in newtons over meters, and m is the distance stretched, and that's in meters. Okay, so force is equal to k times x. K is a spring constant, and that's different for every single spring because it's based on how rigid or flexible the spring is. So the spring in your mechanical pencil has a very low spring constant because it's very easy to compress. The spring in the shocks of your car has a very high spring constant because it's very difficult to compress. So we're going to use graphs in order to look at spring constants and restoring forces. The graph on the left shows the old relationship between force and distance. The force stayed the same as the distance increased. So if you pushed a broken down car on the road, you were pushing with a constant force at every second. As the object travels the distance, the force required to move it stays the same. So down here, as distance increases, the force stays constant. It's not changing. The graph on the right is going to show the relationship between the force and the distance when a spring is stretched. As you move a certain distance, it requires a higher force to move the spring. So if you're not moving at all, the force required is 0. If you're moving 1 meter, maybe the force is only 1 newton. 2 meters, now the force is 2 newtons. So this creates an increasing sloped line. As distance increases, the force required also increases. So again, here's our force versus distance graph. And the slope of this line on this graph is the value of k, or the spring constant. So if you can calculate the rise over run, you can calculate the value of the spring constant. The work is defined as the area under the curve. So the amount of work done as you stretch that spring is the area underneath the curve. So the area under the curve is the work. And since this is a triangle, we can use the equation 1/2 base times height. But the graph shows specific units, so I'm going to replace that equation with the units that the graph is showing. So work is 1/2 base times height. The base is on the x-axis, which is the distance, so 1/2 distance. The force is on the y-axis, which is the height, so I'm going to replace height with the force value. So this is our new equation for work. 1/2 x times F. Now I'm going to rewrite that at the top of the slide. Work equals 1/2 x times F. A lot of times, if we're not given a graph and we're given an equation or a word problem, the force isn't given directly. you would have to calculate it using the restoring force equation from this earlier in this video. So then we would substitute 1/2 x times kx, which is that equation from earlier. We're just making another substitution. Now, I don't like parentheses, they make my head hurt, so I'm going to distribute some information. That 1/2 x can be distributed in to the k, and it becomes x squared. So, does this look familiar? Because it should. The work is equal to the potential energy elastic equation that I gave you in the earlier videos. So our work and our potential energy are exactly the same. Just like in the last video, our work and our change in kinetic energy is exactly the same. Because work is always equal to the change in energy. So using these graphs, you're going to be able to calculate a few things. You're going to be able to calculate the k value, which is the value of the slope. You're going to be able to calculate the work done, which is the area under the curve. And if I give you a weird value, maybe up here, you would then be able to calculate the work done in that scenario because it's now a larger area under the curve. So now that we have the graphs talked about, let's do some math. A 4 kilogram mass is suspended from a spring and produces a displacement of 20 centimeters. What is the spring constant? So our equation is force equals k equals x equals, and we have force equals k times x. Now it's suspended from a spring, so this is what the picture looks like. So the force pulling down is actually the force due to gravity, and I'm going to calculate this using mass times gravity. So the force is 4 times 9.8. K is my question mark, and my x is 20 centimeters, but I want that in meters, so I'm going to put 0.2 meters. 4 times 9.8 is 39.2, so I'm going to plug in 39.2 equals k times 0.2. And to rearrange this, I'm going to divide both sides by 0.2. And my k value is 196 newtons per meter required to move that spring. So that's my final answer. The second example problem. What work is required to stretch a spring of 196 newtons per meter from a distance of 0 to a distance of 30 centimeters? So now I'm going to do the work, k, x, and my equation is w equals 1/2 kx squared. So my work is my question mark, my k is 196, and my distance stretched from 0 to 30 centimeters is 0.3 meters. So work equals 1/2 196 times 0.3 squared. And my work required is 8.82 joules. So here are two possible example problems that you're going to be using with Hooke's law and with the idea of work being in the area under the curve. You're going to be calculating unknowns once given these equations. So I'll see you in class so we can practice this and then introduce a lab that's actually going to investigate Hooke's law. See you then.